Hey everyone, in this video we're going to look at solving a quadratic equation, so no graph to help us this time, that doesn't have what's called a linear term using something called a square root. So obviously a lot to talk about going on in that objective. Any expression that we have that contains one of these square roots is what's called a radical expression, and we're going to have to look at the best way to write those, so a way to simplify those expressions. So a square root is not a root from a tree that's squared, but rather something kind of new we're going to talk about. And I want to set up why it is that we need this thing at all, because it may not be obvious. So when we're solving an equation, we want to find the value of a variable of the variable rather, that makes the statement true. So for example, in this equation, 3x plus 2 equals 8, what I'm going to do is I'm going to try and find what number I can replace x with so that this side of the equation equals 8 to match that side. And in order to do this, I use something called inverse operations. So I want to do the inverse of adding, which is subtracting 2, and that leaves me with 3x equals 6. Then I want to do the inverse of multiplying, which is dividing, and then I get x equals 2. So there I go. Now I've got my solution, and just as we saw in the previous video, I can substitute that back in, and it does in fact make it true. So the question then becomes, knowing all that, how do I deal with this? Because I can go through and I can undo adding 2, that's no problem. And so I would get 3x squared equals 6, and I can undo multiplying by 3, and that would give me x squared is equal to 2. But the question is, how do I undo squaring something? And that is why we need this new operation called the square root. So inverse operation pairs, addition and subtraction undo each other. Multiplication and division undo each other. Squaring and the square root undo each other. So if I've got x squared, and I take the square root of it, which is this symbol right here, the squaring, which is in red, and the square root, which is this symbol here, undo each other. So the square root of x squared is x. So the answer in this previous one to how do I undo that squaring to get the x by itself, well, I have to take the square root of it. The square root of x squared would be x, and whatever I do to one side, I've got to do to the other. And so that is what I'm looking at when I go to solve these. So let's talk about this symbol for a second, because I could see where this you could be confused. It could happen. So this symbol that indicates to us that we're taking a square root is called a radical. So this check mark thing that's in front of this x is called a radical. And the part that's underneath is called the radicand. So when I refer to a radical expression, I simply mean an expression that has this radical in front of it, and then the radicand is the part underneath. I don't think you actually will ever in your life need to know this, but the bar over top is actually a separate thing called the vinculum. So each one of these parts has its own name. You just need to know that the checkmark looking thing is called a radical. The part underneath it is called the radicand. And when you take the square root of a number, it's unlike addition and subtraction and multiplication and division, where you do that and you get an answer and that's that. When you take the square root of a number, you could end up with two answers. So if you're taking the square root of a positive number, the square root of positive 4, square root of positive 9, you're going to end up with two answers, one positive and one negative. The reason is this. If I take, let's say, the square root of 9, what I'm asking for is what number times itself will give me 9. And so the answer seems obvious, 3, because 3 times 3 would give you 9. Here's another way of looking at that. 3 squared and 9 are the same thing, but squaring and taking the square root undo each other, so the square root of 9 is just 3. But let me ask you, if I take negative 3 squared, that is negative 3 times negative 3, isn't that also 9? And when I undo that, I could get negative 3. So the square root of 9 could be equal to 3, or it could be equal to negative 3. You'll sometimes see that written all in one go. Like this, we would say the square root of 9 is plus or minus 3, which means that it could be positive 3 or it could be negative 3. Both are good answers. So when you take a square root, you can get two answers, a positive and a negative. If you take the square root of 0, the result is just 0. So in that case, if you're taking the square root of 0, you'll only get one answer. And if you take the square root of a negative number, you get no real solution. There's not two real numbers that you can multiply together to give a negative. And so what will happen, or there are not two identical numbers, I should say. So what will happen is if you try and take the square root of a negative, you're going to get no real solution. So be aware that we're going to potentially get multiple answers here. Your calculator, bless its heart, will do this for you. All you have to do is press that blue second button and then look for the x squared button. That's kind of catty-cornered to the left of 7. And if you press those two, your calculator will do a square root for you. We can take a look at it over here. So for instance, if I want to take the square root of 9, I can press the second button and the squared button and then 9, and it looks like my calculator is not working. That is unfortunate. There we go, much better. So I can hit the second button and the x squared button right there, and then I type in whatever I want as the radicand and hit enter, and it gives me the answer of 3. Now remember how I told you that had two answers? It could be 3 or negative 3. Your calculator is only going to give you one of them. It's going to give you the positive one, which is called the principal square root. You have to know that negative 3 is also an answer. Your calculator won't do that part for you. So one of the other things we can look at, I can switch my focus back on here, is the fact that now we can just straight up use these to solve. And be aware, again, two solutions, but now you have everything you need to take these four problems and solve them. So x squared equals 196. Yeah, but what does x equal? Well, in order to get rid of that squared, what I'm going to have to do is take the square root. And if I take the square root of one side, I have to take the square root of the other. So x is the square root of 196. Now it'd be nice to have that as a number. Yay, we've got a calculator that will take care of that for us. So we hit second. Oh, I'm still writing. Let me switch over to a mouse here. And if I hit second, x squared, so now that brings up my radical symbol, and I want to take the square root of 196, and there you go, it's 14. And here's where I have to be super careful, because I would say that x equals 14 and be done, and I would be wrong, because x not only can be positive 14, it can also be negative 14 as well. You could also write this, if you're a fan of writing down lots of stuff, you could say x equals 14 and x equals negative 14, but it's better to just write that symbol there because it's a little faster. And here we can do the same thing. N squared, I want to get rid of the squared, so I take the square root of both sides. So n equals the square root of 0, and just to satisfy ourselves that this will in fact only give one solution, when we take the square root of 0 using our calculator, we find that the answer is in fact 0. And since 0 doesn't have positive and negative forms, that's it. The answer is just n equals 0, just one solution. And so on and so forth. I can take the square root of these. So y squared, square root of that will be y. Square root of 81, we can put it in our calculator, but you can also just use your multiplication tables here. we know what number times itself will give you 81. It is in fact just 9. So when I go to write this answer, I can write y equals plus or minus, not the square root of, but rather just 9. Now let's look at this one. I take the square root of both sides, so a is going to be the square root of negative 36. But do you remember what happens when I take a negative square root? Well, our calculator can sure give us an idea of what we'll be looking at. So if I ask my calculator to take the square root of negative 36, notice the error it gives me, a non-real answer. So what this tells me is that since I'm taking the square root of a negative, there is no real solution. There aren't any numbers that I can multiply by themselves and get negative 36. I should say there aren't any real numbers. Algebra 2 is going to be fun. You'll enjoy it. So the ones we were looking at were artificially nice. I chose those examples because they're nice and pretty. Not everything is nice and pretty. Typically, when you take the square root of a number, it's going to come out as not an integer. It's going to have a decimal. And even worse than that, the decimal part will be pretty crazy. When you take the square root of a number, you very often end up with what are called irrational numbers. They are numbers where the decimal part never repeats and never ends. It goes on forever. So for instance, if I'm looking at solving this equation, and I take the square root of both sides so that the squared on the z goes away, and I've got the square root of 10, and then I go and I put that in my calculator. Clear all this out. So I just want to take the square root of 10 and hit enter, and look at the number it gives me, 3.162277766. That number only cuts off right there because the calculator is only giving me that many places past the decimal point. That number will actually continue on forever and ever. There will never be a pattern that consistently repeats, and it will never, ever end. This is called an irrational number. So most numbers, like it is not unusual to get these. Pretty much all the numbers you're ever going to deal with very few exceptions, come out like this. For instance, the square root of 28. So I can just put that in here, second square root of 28, and hit enter. And again, notice the calculator only stops because it's not going to continue pumping out digits forever. And you can even satisfy yourself on this, like put in a bunch of numbers and just see, like try taking the square root of a bunch of stuff and see which ones come out to be even. You'll find that it's a vanishingly small number. So the question is, what do we do with this number that never ends and never repeats? If I round it, I'm losing some accuracy. So what I want to do is something called simplifying it. When we are getting these answers that are irrational, what I want you to do is take the radicand, find the prime factorization, and we're going to move some numbers to the outside of the radical so that the radicand is as small as possible. So let's take 28 as an example. So I've got the square root of 28, and I can take 28 and I can get its prime factorization. Now here's a way to do this on the calculator if you're not real good at just doing these on paper and pencil real quick. So I take 28 and I try and divide it by the first prime number, which is 2, and so I get 14. And then I take 14 and I'm going to try and divide 14 by that smallest prime number, which was 2, and there I get 7. So 28 is 2 times 2, and then 7 is prime, so I can include that and stop. Now, here's where this gets really, really neat. 2 times 2, I can rewrite that as 2 squared, and I'm wanting groups that are the same, that are squared. So can't I write that as, well, 2 squared times 7? Well, squaring and taking a square root undo each other. So it's like I can take that 2 and say that it is no longer included inside that, but rather on the outside. Any pairs of 2 can come to the outside of the radical and live there by themselves, leaving just what's inside. And so the square root of 28 is equal to 2 times the square root of 7. So I've simplified this by making the number inside the radical, the radicand, as small as possible. So let's look at a few examples of these, and then we'll be done here. I realize this is a long video, but there are a lot of important concepts here. So with r squared, if I want to find out what r is going to be the square root of 54. So what I have to do now is get the prime factorization of 54. So if I take 54, that is 54, calculator. So I take 54 and I try dividing it by 2. That works. 27 is not even, so I can't use 2 again, so I'll try 3. And I can divide by 3 again. And that gives me 3 as an answer, so that's prime. So what I see is that 54 is really 2 times 3 times 3 times 3. And so what I want to do is I want to find groups of 2 right there. That's 3 squared. That 3 squared, remember squaring and square roots undo each other, so I can bring that 3, or that group of 3's rather, to the outside, and inside that just leaves 2 times 3, which is 6. So r squared, the square root of 54 is going to simplify down to r equals 3 times the square root of 6. So let's look at this one. K squared, take the square root of it, that's going to make it k, and I've got the square root of 108. So I need to get the prime factorization of 108. Calculator to the rescue, here we go. So I'm going to take 108. Not so good at getting those first numbers, huh? And then I'm going to divide that by 2, and that gives me 54. And hey, wait a minute. I already know the prime factorization of 54. We just did that. So I get 2 times 2 times 3 times 3 times 3. If you're wondering where this comes from, I know that 54 is 2 times 3 times 3 times 3. And so once I see that number pop up here, there's its prime factorization. Or you could just go through the whole process, whichever makes more sense to you. Meanwhile, back at the ranch, I'm looking for groups of 2. We've got it there, and we've got it there. So those are going to come to the outside of the radical, and if I have multiple ones, I multiply them together, and left on the inside is just a 3. 2 times 3, of course, is 6. And so the simplified radical is 6 times the square root of 3. So let's get our last ones here. W squared, I need to make it a W, so I'm going to take the square root of both sides. So I get that W is the square root of 20. I need the prime factorization of 20, and if we work that out, what we'll find is that it is 2 times 2 times 5. Take anything that we have as a pair, and it moves to the outside, and voila, there you go. You have simplified the radical. And then for the last one here, take the square root so that we just get p is equal to the square root of negative 12, and then just stop right there. The square root of a negative yields no real answer. You got to watch for that always, so there's no real solution on this. So to recap, to undo squaring, we use a square root, and that symbol is called a radical. The number that we're taking the square root of is called the radicand. If the radicand is positive, we'll get 2 answers, a positive and a negative one. If the square root is just 0, we get 1 answer to that, which is just 0. If we're taking the square root of a negative number, we get no real solutions. And more often than not, when we get solutions to these, they're going to be irrational. So we want to simplify them by making the radicand as small as possible. So to do that, take the prime factorization of the radicand, find all the duplicates, move them outside the radical. Thanks for hanging in there. I know that was very long, but this is sort of the key concept of this entire module. So if you can get this, you should be in good shape. Good luck, my friends.